Okay, so today we're going to carry on with chapter 5. So we're going to specifically start with section 5.3, which is inverse functions. All right, now this is something that we kind of touched on in pre-calc, but we're going to go through it again and learn more about inverses and how they work. So we'll start by noting that an inverse function is one in which the domain and the range have been reversed. In other words, here is a very, very simple case where we have f of x equals x plus 3, and which of course is a straight line. And they're giving us just a few cases, a equals 1, 2, 3, and 4. And then b, so what they're saying is that if the function is f of x equals x plus 3, and a is the set a 1, 2, 3, 4, if for some reason we're only interested in those values, then of course the corresponding values of y or f of x would be. So in the first case, we're going to have, actually I can write it this first. And clearly that is just, in the first case, we have 1 plus 3, then we have 2 plus 3, 3 plus 3, and 4 plus 3. Okay, so you can think of this as the domain and the range. In order to come up with the inverse, the function will look like this instead. Now, at the moment, we don't know what that function is, but we do know that in that case, a would become 4, 5, 6, and 7, and b would be 1, 2, 3, 4. Okay, so in other words, you are reversing the roles of the domain and the range. And so, yes, and f, the symbol f inverse, that little -1 is meant to represent the inverse of f of x. Sometimes you see that symbol used for, let's say, arctangents, and remember in the trig functions, arctangent, arccosine, and all those, and that's because those are also inverses. So it's not that unusual to see that notation used. Inverse, we raise it to the -1 power. Now, what they have not discussed with us here yet, though, oh, and one more thing I do want to mention here, that we can represent this function as a set of ordered pairs. F of x would be the set containing 1, 4, 2, 5, 3, 6, and 4, 7. And then F inverse would be the set 4, 1, 5, 2, 6, 3, and finally 7, 4. Okay. Now, again, we still don't know what the functional form is for f inverse of x. We know that it exists. Now, by the way, I just want to mention as an aside, they're going to introduce us to a test later on that shows us how do we know if a function has an inverse or not. Now, since we've already seen this in pre-calc, I'm just going to remind you that we can use the horizontal line test to determine if a function has an inverse. Okay, so I'm not spoiling any surprises here. It's the horizontal line test used to determine if a function has an inverse. And how does that work? Well, if you draw a picture of the function, in this case, we have x plus 3. What the horizontal line test tells us that if we draw a horizontal line across anywhere in this graph, let's say right here, it will never cross the function more than once. Okay, in other words, the straight line, no matter what horizontal line we draw, there's no point where it's going to cross twice or more, just once. And so that means that this function passes the horizontal line test, and therefore it must have an inverse. Okay, so that's a geometrical way of testing whether or not a function has an inverse. There are more formal ways of doing it algebraically, but as far as just simply looking at the graph goes, that's a quick and easy way to determine if there is in fact an inverse. And again, if we pass the horizontal line test, we're good. Okay. So anyway, back to this. Also, oh yes, we can use this notation as well. We did this in pre-calc. This is the domain. This is the range. And they're calling the domain A and the range B. So whatever these points are, they're mapped to these points. Then for f inverse of x, the domain would be B, and the range would be A. Okay, so this is just another way of expressing the idea that these are inverses of each other. Now, as far as, and by the way, you might also recall from pre-calc, once we find what we think is the inverse of a function, there's a formal way of proving it. And you can see it right here. It involves composite functions. So to prove or to show that two functions are inverses of each other, it must be true that, all right? So in other words, we have another function which we believe is the inverse of f of x, but we want to prove it. This is how it's done. F of f inverse of x equals x, and f inverse of f of x equals x. It has to be both. If these conditions are met, that proves that these are inverses of each other. And effectively what you're doing is showing that whatever you do the function with f of x, f inverse of x undoes it. Okay, so a perfect example of this would be f of x is x squared, f inverse would be radical x. Because if I take, for example, f inverse of f of 3 is 9, is it true that f inverse of 9 equals 3? The answer is yes. Okay. So this is how we can show that the two functions are essentially offsetting each other. If you apply them both, you're bringing the original value back to x. So that's how we can tell whether two functions are inverses of each other. So we can see by these graphs, of course, but I think the formal algebraic proof is what we really need to see whether or not these are inverses. Also, and they're making the point here that again, you're reversing the roles of the domains and the ranges. So that means that, for example, let me write this out. The domain of f of x is the range of f inverse of x. And further, the range of f of x is the domain of f inverse of x. So like I said, again, we're just simply reversing the two. Okay, so all that being said, Let's see. They're kind of wrapping it up here a little bit. If G is the inverse of F, then F is the inverse of G. Of course, it goes both ways. The domain of F inverse is equal to the range of F. The range of F inverse of F is equal to the domain of F. A function doesn't have to have an inverse, but if it does, it is unique. And that is certainly true. There's only going to be one inverse for each function if it exists. Now, here, they want us to show that these are inverses of each other. I'll tell you what, before we even do that, why don't we remind ourselves how to find the inverse of a function? Okay, I'm sure that's coming up, but I want to remind you about this right now. So in other words, let's take this as our starting point. We'll show algebraically how we got that inverse, and then we'll go back and use the proof. All right. So now this next procedure is based on the logic that, remember, when you invert a function, your reverse intervals of the domain and the range. So if you write this out as, what you're going to do is just swap the x's and y's. Okay, literally swap the x's and y's. It sounds very informal, and it is. I'm sure there's a more formal way of expressing this, but in other words, wherever you see a y, make it into an x. Wherever you see an x, make it into a y. And now solve for y. Whatever you get for y, that is your inverse. So here we have, let's add the 1 to both sides. Divide out by the 2. And then take the cube root. So in other words, if this is f of x, 2x cubed minus 1, its inverse is the cube root of x plus 1 over 2. Interesting. Now, if you want to see, let's see, I'm going to show you a graph. I'm going to try. It's been my experience that SimiLab doesn't seem to do a good job trying to draw two different graphs. Either that or just never figured out how to do it properly. So in these cases, I'd like to turn to something else called Desmos. I find that it does this very well. I'm probably just not using it correctly in SimiLab, but anyway, minus 1. And here we had cube root of x plus 1 over 2. See, I'm not as comfortable. Oh, here we go. Oh, that's good. That worked out rather well. All right, I think we're good. There we go. All right, so now you can kind of see. In fact, let's take a picture of this. Just so that I can write on it. All right, let's get this on. But I think you can see where this is going. There's a symmetry between the two. So the red one is the original function, 2x cubed minus 1. And then the blue one is the inverse, which is the cube root of x plus 1 over 2. So if I were to draw a line through the origin, you can see that there's symmetry from left to right. They're mirror images of each other with respect to that line y equals x. And so that's how I know that they're inverses. In terms of geometry, that's one way I can tell if they're inverses or not. Although it's hard to judge sometimes with these graphs, but it should be clear by looking at it. Once you know what the inverses are, that you should be able to see the symmetry between them. Anyway, now here's how, why don't we do this too? Why don't we double check our results? We can prove that this is correct. Okay, are inverses of each other using composite functions. Okay, so let's see how that works. Now, it's been a while since we did this, so I'm sure we could use some practice. The thing about math is you got to practice. You know, it's like the piano. You can't just say, well, I understand how the keys work. Yeah, practice is everything. So we'll start with f of f inverse. So what exactly does that even mean? F of f inverse of x. It means in the original function, replace all the x's with f inverse of x. Okay, so in other words, you go back to the original function, wherever you saw an x, you'll now replace it with f inverse of x, and that happens to be the cube root of now, of course, the cube root and the cube offset each other. So you end up with 2 times x plus 1 over 2. These cancel out. And there you go. Beautiful. So that one works, but we need both of them. Now we try f inverse of f of x. So go back to the original inverse. Cube root of x plus 1 over 2. Replace all the x's with f of x. And of course, f of x itself was 2x cubed minus 1. Let's go back and confirm that. 2x cubed minus 1. Plus 1 over 2. All right, so be careful there. F of x is 2x cubed minus 1. Then we also have plus 1, and we divide by 2. All right, great. So these cancel out. Then I'm left with the cube root. These cancel out. And I have x. So I've proven that we did this correctly. So we now remember how to find inverses, this procedure where we reverse the x and y. And then we also recall how to prove that they're inverses by showing that the two composite functions bring us back to x. And it has to be both, by the way. One is not good enough. And also, we remember how to test in the first place whether or not a function has an inverse. So if you look at the original function, just the cube root, the 2x cubed minus 1, you can see that red line does pass the horizontal line test. There's no point where a line would cross it more than once. So we know how pretty much everything we need to know about how these inverses work. We know how to identify when a function has an inverse. We know how to solve for the inverse, and we know how to prove that they are inverses of each other. Okay. Now, of course, in a lot of cases, this is a very messy process. Here we have relatively simple functions, but the procedure is always exactly the same. There's other more formal ways too. Let me just throw out one of them right now, because although this is really Calc 2 stuff, but let me just show it to you another way of proving that a function is has an inverse, um, if a function always increases or decreases as x increases, which would mean something like this. You can see in these two cases, as x increases, in the left-hand side, y always increases, in the right-hand side, it always decreases. The function is said to be monotonic. Mono for one, okay? So, and then if that happens, this guarantees that the function has an inverse. All right, so as soon as you see something like that, but I mean, you could also use the horizontal line test as well, but um, this way, you have another way of proving algebraically that a function does have an inverse. So this guarantees that the function has an inverse. Okay, so there's usually multiple ways of proving anything in math, but I just wanted to throw that out there because you'll run into this in Calc 2 anyway. In the fall, I'm guessing. Hopefully, if you wait, you don't want to wait too long to take Calc 2 because you'll start to forget, of course. But if you do take it in the fall, you'll be in really good shape. All right. Anyway, let's go back to this. Oops. God, I've got so much stuff open here. No, that's not it either. Here we go. So yeah, they're proving it to us here. Although they're using g of x for the inverse, but it's the same thing. And oh yeah, what do you know? They did the graph too. So they're inverses of each other. You can see across the line y equals x. The two are symmetrical. They're mirror images of each other. And there's all kinds of results that we can derive from this. For example, if we have two functions that are inverses, any point that we choose at random. Let's go back to our graph for a second. I'll just copy this again. So what it's basically telling us is that no matter what point I pick on the original function, let's just say that on the original function, when x equals, let's say 2, actually, I'll tell you what, let me rewrite this a little bit to make it clearer. Let's call this one f of x and f inverse of x so we know which is which. So f of 2 equals 2 times 2 cubed minus 1. Okay, so in other words, that means on this curve somewhere, on the red curve, is the point 2 comma 15. And all this is saying is that guarantees that 15, 2 is the point on f inverse of x. So we can prove it just by plugging it in. Although, I mean, yeah, you can see it. Maybe it's not so easy to see it on the graph. Let's just prove it. A two. What am I doing? Two, which is the cube root of 16 halves, cube root of 8, which is 2. There you go. So there's your point 15 comma 2. So in other words, no matter what point is on the original function, the reverse of that is on the inverse. Okay, now here they're introducing the horizontal line test. So clearly this function does not have an inverse because the horizontal line crosses it twice. Okay. Now, by the way, when a function does cross the line, sorry, when a function, you may remember this from pre-calc, when a function passes the horizontal line test, it is said to be a one-to-one function. Let me just quickly remind you what that means. You know that from pre-calc, a function simply means each x is associated with exactly one y. For example, this counts as a function because each x is associated with exactly one y. It doesn't matter that two of the x's are associated with two. The bottom line is each x is associated with exactly one y. And that means that this is a function. But a more specialized case of a function is this. A function where, let's go, each x is associated with exactly y and goes both ways. Each y is associated with exactly x. I'll show you a graph of that in a second. Is said to be a one-to-one function and is guaranteed to be to have an inverse. Okay, so in other words, how would that work? So this one is one-to-one because each x is associated with a single y and each y is associated with a single x. That wasn't true up here because 4 was not associated with any of the x's. So while it's a function, it's not one-to-one. This one is one-to-one. So the if this is f of x, then f inverse of x would look like this. That's right. Okay, good. So you can see we just reversed the two. Okay. Now, by the way, being monotonic means the same thing as one-to-one. So if a function is, just as a side note, if a function is monotonic, it is also one-to-one, and therefore, as we saw before, has an inverse. Because being monotonic implies that it's one-to-one. Okay. What about this one? All right. So you can see by the horizontal line tests. Oh, see what they're doing here is showing that it's monotonic because the first derivative, if you notice, is 3x squared plus 1, which is always guaranteed to be positive. And remember, the first derivative shows us how much the function is changing. And so therefore, if we can show that the first derivative is always positive, that implies that the function is monotonic, and therefore it must have an inverse. By the way, we do make a distinction between monotonic function where f of x always increases when x increases. Oh my God, let me make that bigger. Is said to be, it's monotonic, of course, but more specifically is said to be monotonically increasing. And of course, a monotonic function where f of x is always decreasing. And x is increasing or increases. We can probably guess where this is going, is said to be monotonically decreasing. Mono. And there's something about that word. I haven't spelled it right once. Okay, here we go. So let's say, for example, a couple easy cases. I think it should be pretty clear that the one on the left is monotonically increasing. And the one on the right is monotonically decreasing. Okay. And of course, that implies that they both have inverses. Now, very occasionally, oh, what do they have for us here? Now, this one, now look at this one. This is a cubic function. And since cubic functions have this very strange pattern where, well, not strange, but this very interesting pattern where they rise and then they fall and then they rise, you can see that there's going to be at least one point here where it fails the horizontal line test. Okay. So therefore, it does not have an inverse. Okay. And they're showing you that in fact it crosses it 3 times when y equals, looks like when y equals 1. Yeah, when y equals 1, y equals 1 is associated with x equals -1, 1, and 0. And so it cuts through 3 times. So it does not pass the horizontal line test. All right, so just in general, this is a summary of the rules that we've been covering. First, find out if it has an inverse. Theorem 5-7 is the one about being the function being one-to-one, which guarantees that it has an inverse. And then here we're reversing the x's and y's and solving for y. and noting that the domains and ranges are reverses of each other, and then we can prove the results with the composite functions. Okay. Here's a challenging one. F of x equals radical 2x minus 3. Now, I've already done all the work for it, so let's just get some practice. And you can see the symmetry is with respect to this line y equals x. The two are mirror images on either side. So first, let's go back to radical 2x minus 3 and run through the analysis. So first, if you look at the graph, it looks like this. So if you notice, of course, we can't have a negative square root. So if x is 3/2, that's fine. That means x has to be at 0 or greater than that. Okay, so the domain is everything from 3/2 up to infinity. And remember how this notation works. The square bracket means this includes the 3/2. Okay, so it looks, now remember, and also square root is a function that increases at a decreasing rate. So it looks something like this. So you can see visually just by looking at it, it is clearly monotonic, although there are formal ways of proving this, and therefore it has an inverse. It clearly passes the horizontal line test. So why don't we go find the inverse? And by the way, if you try to use that technique we've been learning about finding inverses and try to apply it to a function that doesn't have an inverse, you'll discover pretty quickly that it's just not working. Okay. So let's do what we normally do, which is to say, let's write this as y equals radical 2x minus 3. And then we'll swap the x's and y's. And then we have to solve for y. So we'll square both sides. Okay. X squared plus 3 over 2 equals y. And then, of course, we can prove it. And yes, that is the right answer. We can see from the graph. And then we are claiming that the inverse is right. So we'll start with f of inverse of x. So the first one is f of inverse of x. So in the original function, wherever you see an x, replace it with f inverse of x. Okay. And therefore, and remember we showed that this is x squared plus 3 over 2. Okay. All right, so where does that leave us with? All right, so that one works. And how about f inverse of f of x? All right, so let's just quickly remind ourselves, these are the functions. So therefore, f inverse of x, f of x would be go over to the inverse function, replace all the x's with f of x. And then make the substitution. All right. So of course, the square of the square root is just the original value. And we did it. So we proved both directions. Okay, so we've proven, we not only found the right inverse, we proved it. And then they have the graph waiting for us. All right, and then go through all the steps. Now here they're asking us about the sine of x. Now you know that the sine goes through all these phases, and clearly, if you just took a quick look at the graph, you can see that clearly it does not pass the horizontal line test. Therefore, it does not have an inverse, and it's certainly not one-to-one because many different values can have the same sign. Now, derivatives. Ooh, now we're getting somewhere. Let f be a function whose domain is an interval I. If f has an inverse, then the following statements are going to be implied by this. And by the way, if you notice that in this case, the domain is some interval, the interval could be the entire real number line, but it doesn't have to be. If it is, if it does have an inverse, then if it is also continuous on its domain, that implies that the inverse is continuous. If f is increasing on that domain, the inverse is increasing. If f is decreasing on that domain, the inverse is decreasing. If f is differentiable at a point where the slope is not zero, then so is the inverse differentiable at that point. Okay, but as long as this is true. So I'm sure they're going to show us several examples of this right now. Okay, I guess they want us to do this on our own. So f of x is x cubed. Now they're not even asking us to show or find the inverses. Yeah, that's the cube root. So these are inverses of each other. Want us to find the slopes. Okay. One, 2, 8. We'll do this first, and 327. And then, oh, I see what they're saying. All right, let's do this first. Now, clearly, the first derivative of x cubed is 3x squared. So at that point, 1, the slope is 3. We have 12. All right. Then they want us to do this, the reverse. Find the slopes of g of x at, now, if you notice, not those points, but the reverses. Okay, the first one is the same because it's 1, 1. Now remember, because g of x and f of x are inverses of each other, that guarantees that these points exist. So we have 1, 1, 8, 2, and 27, 3. G prime of x, since g of x is x cubed, it's going to be x to the 1/3. This is x to the 1/3 power. You can use the power rule then for derivatives to determine that g prime of x is 1/3 x to the minus 2/3. Okay, so remember how that works with derivatives. If you have x to the n power, the derivative is nx to the n minus 1. Let me just put that in there, a little note here. Okay. So therefore, g prime of 1 would be simply 1/3 times 1. Okay. G prime of 8 All right, so you could, now there's a couple of ways you could do this. You could put it in your calculator. 8 to the minus 2/3 power is a quarter, 1/4. And then g prime of 27 is 1/9. So they want us to compare the two sets of results. So let's see if I can copy these down here. So you can see the point they're making here. The derivative of the original function at point 1 is 3, and the inverse is 1/3. Here we have 12 and 1/12, and here we have 27 and 1/27. So in other words, I think they have a graph here. Let's look at, oh, maybe not. I'll tell you what, let's go do this in Desmos. Wow, now that's interesting. You can see the symmetry there. So let's say, for example, let's pick this case. Actually, let me take a picture of this. All right, and let me just label it correctly. This is the original function. Here's the inverse. So let's say the point they were interested in was 2, 8, let's say. All right, so for f of x, the point is 2 comma 8. Oh, that's way over here. I didn't grab enough information. All right, but anyway, um, let's say it's here. No. All right, it's going to be very difficult to draw this properly, but what they want you to see is that the results are inverses of each other. That was the whole point of this exercise. But they also want you to see that something strange will happen at 0. And that something is that this will be the same for both of them. Okay, and that's you can see right there because they both cross at the origin. All right. Now what do they want us to do? Oh, okay. So this relationship holds if, of course, f of x and g of x are inverses of each other. It's kind of it might be a way of finding a shortcut. Let's say that you have a horribly messy function f, and you need to calculate the derivative of its composite function or something. Then you might be able to use this result to simplify your results. Um, let's add this to our list. Yeah, that would be the main reason for this result, to show if there's possibly a way to simplify our derivatives. We're always looking for opportunities, as you know, to simplify our equations whenever we can. So also then there's a caveat here that this can't be 0, otherwise we'd have division by 0. But other than that, these should work. So let's see if they have an example for us. All right, here we go. So f of x equals 1/4 x cubed um, plus x minus 1. And they want us to without writing a formula, find f inverse of 3, meaning the inverse. So what they're basically saying is don't find the inverse, but solve for 3 anyway. Okay. So the derivative is, and of course, this is going to be greater than 1. So therefore, it is monotonically increasing. Right. Now there's a function whose curve has a positive slope throughout, is monotonically increasing. That means it does exist an inverse. But what they're saying is that we don't need to solve for it because f of two. First we have to solve for f of two. So therefore, based on this theory, f inverse of three is two. So in other words, f of two equals three. This is what they're telling us. Since f inverse of one exists. Once we prove that that exists, then we can do this. Since f of two equals three, f inverse of three must be equal to two. And we could certainly prove that by taking the derivative, actually finding the inverse, but this makes it unnecessary. Well, I mean, so they went ahead and solved for the inverse. Okay. And these are the graphs. And yes, they want you to see the reason why this worked is because um, we have 3, 2, and 2, 3 here. All right. Let's see. All right. So this is what they were saying before, that G prime of X is 1 over F prime of G of X. And so let's see. Graphs of inverse functions have reciprocal slopes. All right. Well, that certainly makes sense. So let's demonstrate that. F of X equals X squared. Is that again the graphs of inverse functions? Have inverse slopes. It certainly makes sense. So the example they gave us is f of x equals x squared. We're only going to consider positive values, though. Should be clear that the inverse is radical x, although we could certainly prove it if you want to. But what they want us to notice is that the derivative f prime of x is 2x. F prime of, let me see how they use that notation. Oh, I see what they did. Okay, sometimes the notations can be different from one book to the next. You wrote it like this. All right. Oh, so they randomly chose the 0.39. Okay. We're going to apply 39, and then, of course, that implies that 93 is on f prime of x. So at that point, f prime of 3, it's 6. F inverse prime of 9 is that's one of a radical 9. All right. So this is what they wanted us to see. Since 3, 9 is on f of x, 9, 3 is on f prime of x. F of 3, therefore, is the inverse, whatever that number is, which we know is a 6, is the inverse of the inverse of 9. Okay, in other words, this is 6. Okay, that's what this is all about. Again, it's an interesting result, but the reason why you might want to use this is because it might help you take a problem that's horribly complicated and replace it with something a little bit simpler. Okay, so yeah, a lot of these results are there because or go of them because they're not only interesting for their own, but because they can help us reduce the complexity of a problem that we might be working on. And then these are the graphs, so you can see here's the 9, 3. At that point, the slope is 1/6. Here's the 0.39, and at that point, the slope is the inverse, which is 6. Oh, not sure what they want us to do here. Well, we know we already saw this earlier because I drew it in Desmos. This is, and we know that the inverse is y equals x cubed, and that would have to be this one. Okay. And then here they just want us to find the function. Okay, whoops. So let's take a look. Let's we know how to do this. All right. So in other words, remember how this works. Y equals radical 5x plus 4. Reverse the two x and y. X equals radical 5y plus 4. And then solve for y. All right. So, oops, what just happened? All right. So we're going to square both sides. Solve for y, remember. X squared minus 4 over 5. Yeah, it gets slow. Sometimes it gets really slow when we're online like this. Um, X squared minus 4/5. And that means it's C. There you go. All right. So that was our discussion about inverse functions. It was pretty intense, but it was very important. So that was 5.3. So next time we're going to do 5.4, of course. 5.4 is exponential functions, logs and exponentials. We're going to be learning how to take the derivatives of logarithmic functions and exponential functions. It turns out that they're surprisingly straightforward. We'll be pleased to hear. Um, and by the way, the natural log of x and the x are inverses of each other. So that will explain a lot of the results that we'll see in here. We're also going to do integrals for both of them. All right, so we'll say that for next time, and I'll see you then.